Okay, this is a Landsat photo of Africa. What you can see is the Mediterranean Sea, and the red circle or red ellipsoid, it will be our area of focus. And of course, to the south you have the great North African and Middle Eastern Sahara sand sea desert. Now, there's a reason why they call Africa a dark continent, but most people don't realize it really is dark. Look at Europe, and this is actually an old photo, compared to Africa. It's especially along that Central African bight, there's almost no light at all. So what it shows you is just not much infrastructure in those areas and not much electricity burns at night. This is the Paleogeography of Eurasia. That's southwestern Asia and Europe, during the Oligomycene, which is Chatting Aquitania, around 22 million years ago. The carbonate deposition areas are indicated by the light blue brick pattern. You know that where it says EM there, that's the Eastern Mediterranean. And you're starting to see Italy starting to form there. It goes all the way down into the Indian Ocean. You can kind of get an idea where and also the Red Sea rift zones. We fast forward a little bit. Now we go to the late Miocene Mesidian time. That's when the salt was, we had a low stand in the Mediterranean Sea, and salt was deposited in the Mediterranean Sea. It's about 6 million years ago, very late Miocene. Again, you take a look at the brick patterns on the carbonates. What this talk will concern. For the most part, oil and gas companies exploring for hydrocarbons in the circum-Mediterranean area, that post-Paleozoic petroleum systems and carbonate reservoirs, focus their efforts upon shallow to intermediate depth Paleogene carbonate reservoirs, intermediate depth Jurassic and Cretaceous reservoirs, and very deep Triassic reservoirs. Examples of these would be giant gas and sulfur fields onshore France in the Aquitaine Basin. It's in Jura Cretaceous carbonates, Malota Field, onshore Italy, it's pooled in Triassic and Jurassic carbonates. Casablanca Field offshore Spain, pooled in lower Cretaceous carbonates. Indusar D, giant oil field offshore Libya, pooled in upper Paleocene carbonates. And El Bibain and El Buri Field offshore Tunesia and Libya respectively, just in the general zone, Eocene carbonates. So you get kind of a broad area of production, but what's really changed everything is Zour field. Zour fields will ultimately produce 21 to 20, I think 21, 22 or more, 21, 27 TCF of gas. It's pulled primarily in Miocene formation carbonates. This caught many geologists by surprise, although when you look at the regional geology, it's not as surprising as you'd think. It's a different kind of field and a different kind of plate tectonic situation. But it shows you open-minded people, and the people at NE are very open-minded. They're open-minded enough to drill this thing and find this field. This one field, NE, by this Zour field, will supply all Egypt's gas for the next 20 years at least. So we move our way around, and what you'll see here is significant oil and gas fields discovered in carbonates around the Mediterranean Sea. At the left, you start out with Cape Juby Field in Jurassic, Assyria fields, the Ruhr Basin margin oil fields, and these for pretty much at this junction are small fields. And then you go over to Casablanca and the Amposta oil field offshore southeastern Spain on the southwest side of the Pyrenees, and you jump across the Pyrenees and you get Lac and Saint-Emilion fields, which are very, very huge gas fields. Then you go into Italy, and come around the Horn in Italy, you have these collision zones in Italy, and you get Tertiary and Mesozoic, and a whole bunch of fields there. You come around into the fields there, Pitacata, I guess, oil field, and then down into Sicily. Work your way around the Horn, you get some discoveries in Greece and some in Turkey, but these have not been great discoveries. And then you keep coming around, you come through Israel, there have been some oil discoveries there, some of them significant. Western Desert in the Jurassic Cretaceous carbonates. Paleocene carbonates there in Idris A and D fields. Again, back to El Bibain field in Tunesia and Zour field in offshore Tunesia. Keep moving. Unconformities are very important for carbonate sequences. Why? Especially in foreland basins, because Paleozoic soil zones deposit or major unconformities generate significant carbonic acid movements as meteoric waters pass through them during rainfalls. Consequently, you get a lot of karstine. And karstine occurs along jointing where you often get the best production. Example that would be Renchu Field, China, or the mega giant North gas field in Crador, which is actually the biggest gas field in the world. They also focus dolomitation to subdation limestones. I'm not sure for the reasons for that. I think they're still working on that. That's the Great Cambridge Carbonate Bank, discussed by Mr. Sternbach. And also rapid continental shelf seaward subsidence ensues, that ensues major unconformity development leads to ubiquitous shale-prone hydrocarbon source rock deposition. What you're doing as you have a collision margin, and as the outer shelf on the opposing margin gets drawn down into the Arc Trench gap there, what happens is you get what's normally a very narrow zone of source rock deposition along shelf margin becomes millions of square acres. Or square miles, and you get huge source rock development. And that's what you have in the Woodford shales in the mid-continent, Permian Basin, Appalachian basins. It's a combination of the hydrocarbon source rock deposition above this unconformity, basal 40 unconformity along society 40 margin, enhanced reservoir development and subjation reservoirs leads to sub-unconformity migration pathways for subsurface fluid and gases, including hydrocarbons. All these tell you why 2/3 of the oil and gas pooled in the world that's recoverable occur in foreland basins. This becomes important, and actually most of the reserves we see in the areas we're going to look at right now are in foreland basins, some along the mobile zone, some in the stable flowing. So you got areas of movements in foreland basins. The area of interest there again is the Mediterranean Sea. You got the Alps on the left, the Himalayas on the right, different petroleum systems. But just to kind of get you an idea is how big that collision margin is. Then we go back and we look at how foreland basins relate to the oil fields, and this is mainly Western Mediterranean. I didn't really focus on the Eastern Mediterranean. And what you can see is the Ruhr Basin, the foreland basin stable flank fields, Lac Field in Pyrenees Basin of France. You see a similar situation in Italy where sometimes the frontal fold contains the oil and gas, sometimes it's the area in between. And you come back around to Elbe Bain Field. Okay, now we go to the Pyrenees. This is what the Pyrenees looks like in cross-section. There's two cross-sections. There's one down to the northwest and one basically to the southeast. I have to use my pointer here. I think this one is the top one, and here is the bottom one there. You get an idea of just how big that collision margin is. Aquitaine Basin sits over here. I think the Ebro Basin sits over here. Then we take a look at the Lac Field and its position in this Aquitaine Basin. The Aquitaine Basin is basically all this. You have Prentice Basin deep over here, and you got the Lac Basin 4 deep over here. Two big fields front that, and they sit along peripheral highs and formed along that collision margin. One is Saint-Emilion, and the other one is Lac Field. Here's an idea of Lac Field, what it looks like here. Main production comes from this zone down in here. By the way, as we go through these slides, I don't like to show nonconformities always the same color because it gets totally confusing. So what I've done is I've put the upper Jura Cretaceous nonconformity or basal Cretaceous nonconformity as orange, and the top of Cretaceous or basal Tertiary nonconformity is red. So when we go through these slides, you'll get an idea how these different basins perceive this nonconformity, how it's affected things. Bulk of production comes down here in the Neocomian. I'd say some of it's here, but the bulk of it's down here in the Upper Jurassic because the Upper Jurassic carbonates were exposed, again, karstine. Minor for production up here is mostly oil. Move around, and here's a cross-section of that basin. You can kind of see it sits on a peripheral high. There's our carbonate reservoirs here. Some of them, most of them Upper Jurassic, some of them are Neocomian. You get marls for cap rocks, lower Aptian. And then right below this unconformity, you're also getting some oil here in Upper Cretaceous carbonates. Again, this is the overthrust belt associated with the Pyrenees here coming through here. This cross-section here is this cross-section here. It gives you an idea of just how much closure there is in that field. Those are 500-foot contours, people. The only reason that field is not a lot bigger is the reservoir is okay, but it's not great. It's just huge field. And it runs on depletion drive. The gas is sour. It's so sour that it was one of the biggest sulfur-producing units in the world. It essentially shut down a lot of the global sulfur production because it had so much sulfur. 9 TCF of gas in that field, plus many tons of sulfur. Now go back, here's a strike line drawn along that 4 deep margin, and what you see is the relationship, these two unconformities and the wedges they create. Again, you see where the focal point for migration has been along these unconformities. You see carbonates above producing, the carbonates below producing. The reason why the gas is here, this is the deeper part of the 4 deep. Now we move to offshore Spain. We've moved to here now. We were here. We've moved down to here. We're going to look at all these discoveries offshore Spain. I think it's like 6 or 8 of them. The one we'll talk about is Casablanca here. It's probably the largest one. And here's what it looks like. Here's a seismic line across it. That seismic line, I believe, is this line right in here. And then you got a cross section here, across it through here. And what you see, again, our red is our basal tertiary unconformity, and you have Cretaceous and Jurassic rocks exposed and karsted below the unconformity, and that's where you're getting your oil. And this is the actual map of the field. Move along, this is produced, let's see, here's a, now, remember I told you get great porosity right below the unconformity. For the first several hundred feet below the unconformity, you start to get great porosity because of those carbonic acids coming down through and leaching that. Remember you had soil zones up in here, and through that soil zone, the meteoric water was percolated down through and removed a lot of carbon in here, displaced it farther down the reservoir. So here's your really great reservoir right below the unconformity. By the time you get down here, farther away you get, worse it gets. Something to indicate. And here is a cross-section of the unposted platform here. Gives you an idea of how it works. Here again is my top of basal tertiary unconformity coming down through here. Here's my upper Jurassic unconformity coming through here. And what you see is these carbonates are highly eroded right through there. And you can see the karstine over here in this slide right through here. Now, again, your Jurassic unconformity is here. They don't show it to be a big unconformity, but probably is just not a lot of truncation at the unconformity surface. Keep working our way around. Now we're into Italy. Italy gets more complex. There's a lot more exploration in Italy than there has been in Spain for a lot of different reasons. Here we're going to take a look at two things. Look at the strat chart on the right. And what you see is basically a biogenic gas play in the shallow section and a deeper thermogenic gas and oil play in the deeper section, starting with mainly with the Cretaceous and Jurassic carbonates. It goes all the way down into the Triassic. In fact, you've got some big fields in Triassic reservoirs themselves, which is unusual. Triassic is not considered the great producing reservoir throughout most of the world. And also, you get these heavy oils in Sicily, but the oil, all this is thermogenic gas and carbonates. Over this, these are actual oil zones. Remember, the Italians do everything backwards. Their oil is red and their gas is green. So you have to kind of keep that in mind when you're looking at these. So what you see is the major thrust zones here. You see the location of these relatively large discoveries. Melosa here, not so big there. These have become very big, and they exploited these, I believe, in the 90s or so. And then down here in Sicily, this is mostly heavy oil. We'll talk about that as we go through here. Now, this is an interesting slide because it shows you I've color-coded these zones up here, these regions up here with the regions down here. You see the oil source rocks start out in the Triassic, go into the Liassic, and a little bit in the Cretaceous, but not so much so. And then here, I think you got the Cretaceous boundary down here. I didn't color, I think the Jurassic. Yeah, that should be orange there. It doesn't come in on this slideshow, but I think that's top of Cretaceous. That's going to be the top Jurassic unconformity surface. And you get an idea of the oil percentages in the tectonic domains. The heavy oils appear to correspond to 4 deep and 4 inland basinal areas, but the lighter oils appear to correspond to full thrust belts, which are notorious for leaking hydrocarbons, especially the lighter ones. I think that's what's keeping those lighter oils there. As you keep getting recharged from hot, deep gases. Here's the same thing put us in a regular diagram here. Hydrocarbon generated going this way, depth going down through here. You start out with CH4 up here, which is mainly biogenic, and you go through the geochemical zone down here, oil down through here, and then eventually into gas. You see this is the bacterial gas in northern Italy. Immature oils in Sicily are here. Crude oils in Lombardy, which are better oils. And gas constant is also in Lombardy. Again, this is a tectonic map of the Peri-Adriatic region, and that would be around through here. There's been some exploration over here that's not been real successful. The Italians have been at it longer, and they've kind of found ways to make this successful. Big fields up in here, big fields, I believe, in here, and minor fields here in Sicily. Some of them are actually pretty large, over 100 million barrels. This is the late Triassic facies maps, and these got get an idea of what you're looking at through here, and facies carbonates all through here. This looks like intermontane basins or something here. And then you go to carbonate paleogeography in Triassic, Liassic, and Oxybation. Here's what they look like through here. Now remember, Triassic, Liassic, that's your main source rock, so that's important to know. Italians have put out a pretty good map series for publication because they're trying to get other people to come in Italy and do some exploration. This is early Jurassic here through the end of Cretaceous, I believe, over there. I'm going to go through these rather rapidly because I have a lot of slides. Now we're moving down to Sicily. This little box here is this whole slide right through here. You got a cross section that comes CC prime across the Ragusa Basin, across this overthrust zone in here. Most of your fields sit down in here. This is a very leaky zone, leaks both oil and gas up here. Now here's what that cross section looks like, CC prime. Your main source rocks are here, which is Noto and Nosa shales down through here. That's what your main source rock is. There's your main oil reservoirs there and there, and they're sealed by these marls. Marls tend to be ductile and become very good seals. However, almost all of these are very low API gravity. 14 API, 6 API, 8, 7, 7. You don't explore for stuff like that. It's good for asphalt, not much more. Shoe polish maybe. Now we look at the Maghrebian units and the Cilician fold thrust belts, and this is a basic strat chart here. These are all producing reservoirs, again, maybe mostly lower Jurassic and down in the Triassic. Your main source rock's right in there, so you get an idea. That's the Triassic and actually very early lower Jurassic source. Very good source, and that's the only reason you have this field, heavy oil fields as big as they are. This is a pretty good diagram. Basically, you got 1, 2, 3, 4 cross sections here. This one's in the Po Valley here. You see opposing thrust belts, one being crunched this way and one being crunched that way. And of course, a lot of the biogenic gas fields are in the center of that. And then you come down to the one down through here. Again, you got the opposing thrust belts, one over here and one over here. And then you go further down, and it's more subdued right in there. And here it's almost non-existent down through here, which is farther down towards the Buda, Italy. But remember what's happening from north to south. You're losing the opposing margin, the severity of the thrusting on the northeastern side. Now we're going to take a look at a tectonic map of Italy. We're going to look mainly at cross-section AA prime. We didn't have time to show B prime. It sits right in here. We're going to look across the Melusa field, which is actually a pretty good field. And you'll basically see this field here on a hanging wall incline. And that's what it looks like. But notice it's got 53 API oil, a lot of gas associated with this field. Gas condensate, that's what they're calling it actually. Two reservoirs are dolomitized carbonate platform rocks, the Monte San Giorgio dolomite, Anasian dolomite principale, and these are mainly Triassic, and all this Norian Rhaetian carbonates. Source rocks are anoxic interplatform basins, lows within the basin inner platforms area, and are exposed middle Triassic source rocks. Very good source rock potential there. Okay, this kind of shows what's going on. Here's the biogenic gas up here, BCH4, it's all methane. But down here below the Miller-Mite unconformity, you pick up significant fields. Here's one here, here's one here. So here's the Apennines over here, here's the Alps on the other side. And just take it from the ABG publication. What this diagram shows in a nutshell, I'm not going to go into it in great detail. The more sulfur you get, and the higher gravity you get this. Okay? In other words, the higher the AP gravity, down here you get less sulfur. That's what you want to see. And these are paraffin base oils, I guess. Now this is from this article here, from Italians put it out. And what they do is they show you in these color-coded little basinal areas what you're getting. And what you're getting here is source rocks here in the Gagliano area, or up in here in the Po Valley. And you go to these kind of blue triangle situations in here, get them here, here, down in here, off Sicily. the source right there in the Jurassic, and some actually in the late Jurassic. Then you come into these Via di Agri and Temperosa fields up in here. These are actually very good fields in here. They're discovered late, by the way. These up here in the Paleogene and Neogene would be, I guess there, I can't really tell. And these are biogenic gas there. So you get a big differentiation with depth on these fields. And here's a cross-section of the Apennines intermediate external zone here. And what I'm showing you here is you've got some minor production here in Miocene through Cretaceous carbonates. This was really telling us something, but nobody really understood what it was telling you. You get some Miocene, get a good Miocene seal, and where you get it, you're going to get some hydrocarbons. Here it looks like it's below the thrust and into an old fault block down below. Not too dissimilar, if you look at it, to the Casablanca field. And that's the main thing to say. I'm not going to go through all this because it'll take more time than I have. Now, we got 3 different cross-sections. One goes across Emilio field, which is up in here. What you see is what's called a harpoon structure. You have an old rift basin block that's undergone trampetion. It's ridden up on the deepest part of the half-graben down through here. And you get some gas and condensate production up in here, maybe a little bit of oil. And then you go into this field down here. These are all compression folds. There's one here, there's one here. This one's different down here. This one, the Aquila, which means eagle, I think, in Italian. This looks more like Casablanca field. We get carbonates exposed underneath the unconformity. Just not a lot of closure on that field. So this one, this cross-section's here. This cross-section is here, this cross-section is here. Gives you an idea on the western side of the Adriatic, kind of what's going on in the carbonates. Now, you go to central Italy, more central Italy, and you get this happen. These are big fields in here. Cretaceous, Paleogene carbonates, and Upper Triassic, Jurassic carbonates interspersed with Miocene flysch. And you got imbricated thrust sheets containing rocks ranging in age from Triassic to Miocene. And they've been discovered in this full thrust belt. These 2 fields, Gagliano and Via Fortina, that's the area, ones up to the northwest, just off the Po Valley, produce light oil 34 to 42 degrees, some thrusted Middle Triassic dolomites at depths ranging from 4650 to 62, that's almost 20,000 feet, people. But when you think about it, 4 deeps are kind of cold. So you can even get condensate production that deep sometimes. But again, Triassic dolomite, that's why you're getting those deep production out of the Triassic. Now this is the Via Agri area, and this is this area up in here. You get an idea. It's 600 million barrels in here. This they think is 400 million barrels. These aren't over 1 billion barrels of recovered oil in this area. Here's where it's located. Now this surprised people because they were playing the stuff out here on the offshore side. I mean, they play stuff down here. We had the sea. They play stuff in Po Valley. But somebody gutted up and drilled in here and found some pretty good fields. Again, estimated reserves of 1 billion barrels of oil. Now we come around the horn a little bit. Now we're into the Aegean, and you're almost in Turkey in there. These are seeps. That's the symbol for seeps on the thing here. There's been some dry holes drilled in here trying to chase these seeps, but it's pretty busted up. I think the seeps are telling you it's difficult to make a trap. Anytime you see a lot of seeps, you either have a very, very big field or you got breach traps. This is taken this paper down here. So right now, this looks interesting, but not at bad times. You don't make this play at bad times. This is from a paper in the Oil and Gas Journal. It's actually a very good paper. It talks about the 3 different types of petroleum systems here, A, B, and C. This one is mainly in the Jurassic carbonates, the early Cretaceous sandstones. This occurs down through the western desert area up in here, and actually some here in Israel also. Then you go to the system B here, which is kind of the offshore in the Nile Delta, and then the C, which is stuff offshore Israel here. But what you'll notice here, that you get transpressional through about, I just see here, passive margin here, and it goes like to transpression. So you get Raman reversal in these areas. That's what's causing these fields to develop. This is onshore Israel, Dead Sea. This is a topo map of Israel itself. It shows you the Dead Sea through here. And there are the fields down through here. These are not, for the most part, not big fields, although they've been finding some big ones lately. At least they purport them to be big. You never know with the Israelis because they have a stock market. They tend to tout things a lot more than they are. This field here is supposed to have a lot of a lot of oil in it. It's the Maged area, I guess, like Megiddo. It sits kind of right in here. It's in carbonates and dolomites down through here. Here's a paleogeography map down through here. I'm not going to dwell too much on Israel because to date it's not been real productive, and it's unless you consider Levantine offshore. And also it's kind of interior place, not so much for international oil companies. But we will see essentially here again, see how I color my unconformity. This one's more difficult to determine. That's going to be your red unconformity. This shows you how the Jura Cretaceous unconformity is giving you some leaching below that surface. You see it down here. You also see it here. Again, Jura Cretaceous, base of Tertiary. Now we'll go to the Egyptian onshore, and we'll talk about the western desert fields. Again, this is taken from the OG, Oil Gas Journal paper. It's actually a very good paper. And most of this I already knew, but I hadn't seen it put together this well. You start out with late Triassic, Triassic, Jurassic, Gondwana, transtensional rifting, where you just form a bunch of rift blocks, and these are sands formed along the boundary fold of the rift. Then you go into a subsidence phase, and you get some Jurassic carbonates that go over these rifts. Just post-rift thermal subsidence. This is down here. Then you go to here somewhere, then up into here. And then finally, starting, I'd say mainly in Santonian, but it's not, it's kind of a periodic transpression. Started in Santonian, but actually pretty much went through Laramide time. And you see that mainly in fact, throughout a lot of Africa, especially you see it in Senegal, you see it in the Central African rift system, these transpressional movements which generate oil and gas traps. So, extension, subsidence, transpression, and then you develop these fields here. These look very similar to as what you remember for offshore northeast Italy. Here's the same situation here. You got I think that's an inversion there. Difficult for me to see without my glasses. And passive margin facing through here. Notice this blown up area down here. We're looking at the portion of the western desert. You see predominantly high side fault closures. And you got to figure you would see them down-thrown side down there. More likely than not, they're down-thrown closures. They're inversion structures. But pretty much high side fault closures here in the western desert. Now we're going to the giant Zour gas field. This is the game changer for the Mediterranean. People are still trying to figure out next best place to find another Zour field. Again, it's a 21 to 27 TCF gas. It's about 31 TCF of gas in place. It's all methane. Source rock, biogenic gas, reservoir Miocene carbonate buildups. You get a seal up here, more here in your Messinian evaporites. This is critical. That's what really makes this a big field, because from this direction and this direction, everything just feeds into here because huge reservoir development, very thick reservoir development, and sealed by the salt. Salt's always a good seal if it's thick enough. Now this is an interesting thing. Unfortunately, the guy who drew this kind of made it confusing. A goes to there, that's here, and then B goes to there, which is here. So this is north to the south. This goes from the middle of the Zour discovery down to the southwest. This shows you where the Zour discovery occurs. These are Messinian evaporites above it, cover it. But you notice there's a pre-Miocene carbonate buildup in here. They figure that's, because this is Miocene reefing here, and they figure that might actually be a Cretaceous pinnacle there. They were going to drill that out, I don't know if they have or not, but if they do that, they'll make Zour even bigger because it's not that far from it. Again, take a look at it. This is one of these things where it helps to have a big army and a good navy, because Egypt made things good for themselves. They incorporated that high, 100 square kilometer high. It's not small. So, and it just goes out where the Cyprus bound is. Cyprus gets nothing, Egypt gets everything, unfortunately, for the Cypriots. Again, here's what it looks like in cross-section, seismic line, salt seal up through here. I'm not sure what that surface down in there is. That would be, let's see, that's top Miocene seal. The base of Messinian salt would be, and Messinian salt starts in upper Miocene, so there's upper Miocene salts in there. Here's what it looks like here in geologic commodity salt before else you see it again. Again, sources here, biogenic feeds into that. And here's what a reservoir log across Zour is. And of course, they're trying to impress the Egyptians. Here's how thick the reservoir is. This is the Great Pyramid. 1, 2, 3, 4 Great Pyramids high. That's how thick that reservoir is. I think it's, God knows how many meters. I can't read it from here. But the net pay is just tremendous. That's what they're going to recover from the field. It's actually 31 TCF of gas field, but since it has no liquids to it, they're going to, it's 31 in place, TCF in place, but they're going to get 22 to 27. Great reservoir. This is the kind of stuff international geologists and geophysicists dream of, especially late at night. Okay, now this is Libya. The problem with Libya is these are all bad zones where the terrorists are going crazy around these fields and causing troubles. And again, a similar situation here. So because of this, Libya has kind of gone dormant until they can sort things out. That might take years. Oops, got too aggressive there. Yeah. Okay, we're going to look at this inset map right in here, okay? You have 320 fields in Libya in these different basins, and their reserves are 50 billion barrels of oil and 40 TCF of gas. And this is probably about 6 or 8 years old, this diagram, but not a whole lot's occurred since then because of the problems. Now what we're going to focus on a narrow little part in here. See all these little fields in here look like little dots? Those are pinnacle reefs, but they're very thick pinnacle reefs. They're like mini Zours. And one of these, the Intisar D reef, has about 1 billion barrels of oil recoverable out. We'll see that coming up. But in this trough down here, that's where these little oil fields are. And here's where they are. They built up on upper Paleocene platform here into the Zelt, and they build up like pinnacles down through here. They're very high pinnacles. You get other oils in other areas down through here. I didn't color the lower Jurassic, Jura Cretaceous non-conformity would probably come in here, something like this, and go up and down, because that forms basically your bottom fault, your rift blocks. Keep this in mind. Now we'll see burial curves for this, these different things, different reservoirs. What's interesting here is about mid-Paleogene, where your critical events where everything occurs. Trap formation, overburden, your reservoir source rocks are down through here, seal rocks are down through here. Everything just happens right there. So it was actually perfect for sealing in oil rather than gas. And here's a cross-section just modified from Hardy. I believe this is a USGS thing, but it's actually a pretty good one. And what you see is the carbonate. There's some carbonate production. I'm not going to focus on this. I'm going to focus mainly on that. See that little thing there? That's those little pinnacle reefs that grew up in the Zelton series. You actually have a little bit here trapped below this unconformity here, which looks to be Oligomycene. Okay, here's a bank carbonate in here. Notice you have a little area in here where it's low, in the center of that old rift subsidence. These are all oil fields down through here. They're actually pretty good sized oil fields. What you see there, they're the basal margin of the upper Sabile Zelton carbonates, which is right there. And these fields are forming right there. Porosity in these fields range as high as 35%. This formation exceeds 1,000 feet, and sometimes as much as 600 feet of net porous carbonate. It's like drilling a huge oil can. Defa and carbonates and facies dolomites go up to 400 feet in area. 25 wildcat wells reach these formations at depths less than 9,000 feet. But even then, right now they're probably not underexplored because they've shot 3D over them. Here's what these things look like in cross-section. That's 1,000 feet there. That's all reservoir in there. Here's what it looks like in a seismic section. And what's interesting here is usually under carbonates you get a kind of a pull-up. These carbonates are so porous you actually get a sag below them. Incredibly enough, you get a sag. 5 kilometer circular reef, full to spill 995-foot oil column, 40-degree API oil, paraffinic and low in sulfur. Original GOR of 500 cubic feet per barrel. Stockton oil in base was 1.8 billion barrels, but it's going to produce, what is it up here, 1.35 billion barrels of oil. This is the cross-section for this cross-section of this reef down in here. This is a cross-section for this done at seismic. But it gives you an idea that if the Paleogene carbonates aren't a bad play if you get them in the right situation, especially with a great source. Now we're going to go to the northwestern Libyan offshore and the southern offshore Tunesia. Okay, and what we'll see here is these two charts, and these are the source rocks up in here. Here look like they're anywhere from Aptian, Albion up to Turonian up in here, which is typical. This is your OEE events in here. And then your main reservoirs are up here in the Eocene. I think they're mostly Nucleolithic limestones. We'll see that coming up. Now here's the fields that sit around the boundary here. I believe the oil, they've got this done correct according to U.S. terms. The oil's green, the gas is red. These are discovered. This paper concerned these discoveries here, but we'll talk about L.B. Bain a little bit, and we'll talk about some of these other. Again, here's Tunesia. Some up here is the old city of Carthage. Here's a cross section. It gives you an idea of what's going on here. That's your reservoir, and that's where you're getting a lot of your oil here in the offshore, that Nucleolithic limestone. And then here's the fairway for the oil. Where you have those Nucleolithic facies, you get oil. There's a little oil field that's almost exactly corresponding to that. You get out of that, you may get something, but just not that great. So here again, it's partially a facies-driven trap, so you have to remember that when you make a play. Now we're going to Morocco. We're getting close to the end of my presentation. You got 5 major geological domains. Inside the realm of this talk of this, we're not going to discuss that because that's not too far outside the realm of our talk. The rift domain is the thrust full belt where the deformation of the Mesozoic series decreases southward. Then you got the Atlantic passive margin. It's thick Mesozoic sediments locally formed by salt tectonics and gravity-induced imbrications. But they have some turbidic sheet deposit basinward. They're starting to play. They've been playing those for a while, but no success. Then you got the Meseta here, which is domain characterized by deformed Paleozoic, unconformably overlaid by folded Mesozoic deposit. We'll look at that a little bit, but pretty much to today, Morocco's been not very productive oil and gas. There's a reason for that. The Atlas Mountains, which is your main source rock epicenter, got inverted during the Laramide movement, so all your source rocks above all your reservoirs. And of course, it's leaky as hell. You get a lot of oil seeps throughout the Atlas Mountains. But unfortunately, when your sources are up here, your reservoirs down here, it's difficult for oil trapping. But there's still opportunity if one makes the play right. It's an area where if you sharpshoot, you can find some big fields. 3 major orogenies affecting the Phanerozoic section in Morocco: the Hercynian orogeny, which is Upper Devonian Carboniferous, same one you have over there in the mid-continent area. And over that unconformity developed with that, you get the Woodford shales deposited. But that's in mid-continent United States. This is over here in Africa. Triassic Liassic extension. Opening Atlantic was preceded by Triassic-Jurassic rifting, followed by massive regional subsidence during Jurassic and much lower rotation, Atlantic passive margin. Extension was also responsible for opening Atlas Trough. This Atlas Trough is huge. Alpine orogeny, this is what you're really looking at for the most part here, although you get some salts associated that are pre-alpine. Here again, depends on what you call alpine. Some people dip all the way down into mid-upper Cretaceous time, call that alpine, early, middle, and late. With the middle alpine being actually Laramide, late alpine being Ligamycene. Alpine orogeny mainly during the Laramide movements. Atlas Mesozoic troughs were inverted to form the high and middle Atlas. Late collision of Africa and Europe during the Neogene, resulting in the formation of the rift, not RAFT, rift, a segment of the western Mediterranean alpine fold belt. So we'll take a look at that. Here's the rift. Okay, that's a late forming thrust sheet. And what you see is oil seeps in these little triangles right here. As I said, you get these full thrust belts. They're just leaky as hell. But occasionally where you have good seals, you'll get fields, especially along the frontal zone of the thrust. Here's one at Selfit Field here. Another one over here is Boudra'a over here. And we'll see these in cross-section. Again, the Algreia Sea over here, Atlantic Ocean's over here, and this is northern Morocco. Meseta area is down here. We'll look at one cross-section through Meseta for the presentation's over. These are the Moroccan reservoir signals known to contain carbonate reservoir intervals. Jurassic. Numerous reservoir intervals are also encountered in Jurassic, Reefal carbonates, Missouri Basin, with porosity values up to 10% in Tarfaya-Leone carbonates. Sandy dolomite carbonate of the Calovian and Oxfordian in this Ossuaria Basin, where the porosity values range from 5 to 20%. This is somewhat similar to what you have in the Haynesville and the Smackover. You got the similar problems. You don't always necessarily get your production from the top of an anticline. It's all associated with what was going on, because the reason why is you get salt underlying these carbonates, and it tends to move differently throughout time. We won't talk about the sands because they're not what we're addressing in this talk. Lower Jurassic carbonates in the Grishik Basin, reef carbonates in the high plateau, oolitic limestone and sulfate. We'll see that coming up. Porosity values of lower Jurassic reservoirs ranging from 10 to 30%. 30% is good for carbon. In fact, that's karstic carbon for the most part. Cretaceous, upper Cretaceous rivers were counted in the Tadla Basin. These are comprised of sedimentary trading carbonates. Porosity values up to 10%, and actually above that. Okay, now, remember I told you there was a cross-section that went across the front end of the thrust belt. Here's what it looks like. Here's Sulfate Field up in here, out of the Dogger, I think, through here. These are middle to upper, actually middle Jurassic carbonates here. And you get oil here, oil here. Notice how you got an old Triassic salt series down here, and these folds are detaching along this salt, as you can see. And some of the salt gets incorporated into them. And you got supernat Miocene, because this is a very late forming basin. This is really a Neogene basin. So, but again, these aren't great fields. I doubt if either of them will produce more than 100 million. In fact, I don't think either of them will produce 100 million barrels. Small fields. But if you get to the interior part of the fold belt where you have intact seals that didn't get breached by continual compression, you may get some pretty good sized field. Coming to the end here, now we're looking at a cross section here across Algreia Basin. Down here, I believe, is the High Atlas. Down here, remember I said this is the area where source rock's all above the reservoirs now. And you got gas fields through here. These are the gas fields. Cross section here is this cross section here. Remember how I color coded the unconformities here. This is the top of Jurassic here, and here's the top of Cretaceous. You know, over these salt swells, these two tend to converge right in here. Source rocks are through here, and actually some down in here. I believe those are Silurian shales, yes. Silurian shales, tough. You have to worry about the rifting phase that opened this up, the heat associated with that, heat associated with the old collision, a lot of problems with Silurian. But there may be zones that you have Silurian still preserved as source rocks, and you got migration pathways up along these faults. But the problem is they come up when they hit the salt and stop. So unless you get through the salt, you're going to have a problem. But up in here, you've got this, looks like the Middle Jurassic shales through here, or Torsian to Middle Jurassic shales, Liassics down in here, and Upper Jurassic up in here. They actually produce some oil out of these fields up in here. Some of them are actually decent-sized fields. Okay, last slide. And with this bad cold, trust me, I'm glad to see it. Conclusions regarding these carbonate petroleum systems. And I made this slide up about 3 hours ago. They contain multiple excellent petroleum source rocks. It's led to major oil and gas discoveries in reservoirs ranging in age from Canberra Ordovician, that's in the Hassi Massoud field in Nigeria, to Paleocene, NSRD field. Hassi Massoud field is a Canberra Ordovician. So you produce all the way from the Canberra Ordovician into the Paleocene, and actually a little bit into the Eocene. All the fields aren't as big. But until recently, oil and gas companies exploring for oil and gas in circum-Mediterranean post-Paleozoic petroleum systems involving carbonate reservoirs have focused their efforts mainly upon shallow to intermediate depth Paleogene carbonate reservoirs, intermediate depth Jurassic and Cretaceous reservoirs, and very deep Triassic reservoirs. These are mainly in Italy. So what do we have evidence for this? Again, Lac Field, Jura Cretaceous carbonates, dolomitites there in the lower part. Malota Field, onshore Italy. This is a big field. Pooled in Triassic and Jurassic carbonates. Casablanca Field, medium-sized field, makes around 150 million barrels. Offshore field, pooled in lower Cretaceous carbonates. ESRD, giant oil field, offshore Libya, onshore Libya, excuse me. And that's the one that's got over 1 billion barrels recoverable in it, pooled in upper Paleocene carbonates. And El Bibain and El Bouri fields, offshore Tunisia and Libya, respectively, Eocene carbonates. These are not big fields. Maybe get up to maybe 200 million barrels at the most, and there's reasons for that we won't go into. Okay. World-class giant oil fields pooled primarily in Miocene carbonate reservoirs were discovered decades ago when thrusting hanging wall final anticlines bordering the eastern mobile zone of the Persian Gulf Foreland Basin in Iran. Goshrad oil field, that's like an 8 or 9 billion barrel field. Good example of that. Pooled in Asmari Formation Miocene carbonates and minor subsalt Miocene oils in the Gulf of Suez. But you also have some Miocene oil I believe, in the onshore southern Italy. All these things were telling you something, but it wasn't until Eni gutted up and drilled this Zour giant Zour discovery, producing that much, or EUR is 27 TCF of gas. Most of this caught geologists by surprise. It just goes to show you when you get shows, you just have to find a place where you got a good seal. In this case, Zour just had that Methylene sulfur seal. That's why Zour works so good. Now, unfortunately, it's not oil because maybe that's not bad because of the depth of barrel, but because it's biogenic gas. Any questions? Yes.
So if there's all this oil in the circum-Mediterranean, how come they import so much from other countries? I mean, shouldn't they be self-sufficient?
No, because they're like the United States. They produce they can produce significant amounts of oil, but they use so much more. Like, look how much the United States is one of the biggest producers in the world. I think it's like at least second, if not first, because of all the shale gas drilling. But we just eat so much oil up, we still have to produce it. Now, we're back now to where it was in 1970, early 1970 as far as oil imports. It wasn't due to Obama, it's actually more in spite of him. But that's the key. They suck so much oil, and they burn petrol like everybody else. They have planes that fly in the air, they have trains that drive, and stuff like that. So it's an issue they can't produce enough to do what they want. Remember, the fields I'm showing you, some of these fields go back to the 50s, like the Villarosa field, like that's in the 50s. They're old fields. The Algreia fields, those are relatively recent, I think the late 80s or 90s. And they've tried to do stuff with the Sicilian fields, but 6 to 12 degrees API, that's asphalt, you know. It comes out almost hard when it does come out of the hole. That answer your question? Okay. Yes, Donna.
Good talk. What are the pressures like in the Italian fields?
They'll vary according to where the top of pressure is. One was very high pressure. In fact, that one I showed, I think, in Molosa field, one of those fields where it had, that was in the Lock Basin, Lock Field. Lock Field is a depletion drive reservoir. But it will depend on where top pressure is. If you got thick carbonates that get thrusted up into overpressured shales in the 4 deep, then you get a great seal, which is a pressure seal on top and on the flanks of the trout. But you'll have ways to feed water into it from other areas in the mobile zone, so that may work. The answer to that's probably in my secondary slides, which I didn't show. Actually, it was about 130 slide talk. I cut it down, I guess, about 60 real slides. But there's a lot more that I didn't say because I just didn't want to have everybody go to sleep on me. Yes, Bob?
Steve, is the source rock section on the Zour field same as what they have in the big fields off Israel?
Yeah, Tamar Field, I believe it is.
Are they Miocene?
Yeah, pretty sure it is. It's the off-reek equivalence, silicious classic equivalence of what you have.
Well, there are plastic reservoirs up there.
Right, they're classics there. Here it's carbonates. So what it shows you is when you got a petroleum system that produces that kind of field, why not play the carbonates too? It's all seal related. It's like I keep telling people, you have the geophysicists and they're the trappers. They look for the biggest trap you got. Of course, Zour is great because big oil and gas found in big bumps. And you got the geologists who are the rockers. They pretty much go for the best rocks. But a lot of it's sealers. If you understand the seal and the pressure relationship with your seal, a lot of times you can get small area, horizontal area fields that produce a lot of oil and gas. An example of that would be West Chocolate Field. It's about no more than 2 sections, if that much. It's going to produce like 3/4 TCF of gas plus condensate. So a lot of times it's a seal, not so much what your reservoir is. Source has a lot to do with it too. Anybody else? Yeah.
When it comes to the Zour field, did you find conflicting reports about the reservoir or about the quality of the gas? It seems that there were reports at one time of Cretaceous to Miocene carbonate for the reservoir and sour gas maybe in the product.
Well, I think the first initial discovery was found in Miocene carbonates. Remember I showed you that one slide where it looks like you had Cretaceous pinnacles growing up. They may have drilled that, and I have not seen the evidence of that, but that would have happened in the last couple of years. And again, Zour was not my total focus of this talk. I was doing a whole Mediterranean. But there appear to have been some pinnacles that grew up from deep section that appear to be started early on and grew up into the Miocene. That answer your question?
The gas seems like it's fairly dry, biogenic type gas, there was talk at least of some H2S in Zour gas maybe.
H2S I don't know about. I have to go back and look at the slide to see. It's, I don't remember a lot of H2S there, because if they had H2S in Zour, why would it not have it in Tamar field and those other fields? It's basically the same source. H2S, a lot of times, if it is a situation where it's got H2S, that means those reefs are rooted in very deep section, probably much older than Miocene, maybe down to Jurassic even. And when you get that section down in there, especially in a four-lane basin, you can cook some old evaporite rocks and get a lot of sulfur gas come out of it. So, but yes, right now they're all happy. They think it's mainly C1. As far as I remember, it's low sulfur. But that may change. I'm sure they'd rather not have any sulfur, because you get sulfur with it, that just changes the whole production pattern. It's more expensive, chromium tubulars and all that. Anybody else?
What about the Pyrenees field? That's
Which one?
Pyrenees in Greece, is that Jurassic carbonates?
I don't know. I have to go back and look at it. I've not really studied that
That's
one.
sour gas, and that's sour oil. Which is? Pyrenees field in western Greece.
Bob's worked Greece. That's why he's probably an expert on Greece.
No.
There's some sand fields in Greece too, below nonconformity. But
I forgot. Well, Steve, first off, I forgot to mention Walter Warnock's over here. He's got a poster display on Egypt. So if people have a chance to take a look at that. Again, thank you very much, Easy Core, for your vendor corner. And thank you very much for your unpaid promotion of them. And we have a speaker's gift, which if you've attended HGS meetings on a regular basis, you know it's from a mysterious, unknown, never to be found by mere mortals quarry somewhere in the Austin area of what they call rattlesnake limestone, which is not really rattlesnakes. But it says on the back, and it's a mystery. So, Steve, here's your speaker's gift. Thank you very much.
Bob. If you have any questions regarding stuff farther south along the Northwest African margin, I have data on that I don't show on the slideshow. Again, I cut this slideshow way back to make sure that you guys can get out of here by 8:30. It's 8:15 now. Actually, it's pretty good. About an hour, almost a thousand.